Okay, welcome to the Chapter 1 homework review. So this is the first one of these for the semester, and I will do these every week after a homework assignment has been closed, so I'll typically post these sometime on Monday. So just to give you some information about the purpose of these, so essentially what I do is I will go through Blackboard and look at the results of the homework assignments and try to identify the questions that we had the most difficulty with, the ones that the most people got wrong. Sometimes there's sort of a theme that emerges from that. So I'll try to cover those questions, cover those topics in a little bit more detail to try to help you clear up any misunderstandings that you might have. Now, I did not get any requests this week for questions to cover, but you are welcome anytime during the week to send me requests. I typically put this together Monday morning, so I'll need to get those in by then. But if you have a specific question or a specific topic that you felt was difficult in the homework assignment and you want me to cover it in the review, please let me know, and I'd be happy to do that. Now, the other thing to keep in mind is one thing I'm going to do this year that's a little bit different than in the past is I will be posting this document, both the blank and the completed versions of it, in Blackboard. So if you want to get a little bit of extra practice, a little bit of extra review on this week's homework assignment, I do encourage you to try the problems on your own, either before or after watching the video, and then see how you do on those. And you might get some questions in there that you didn't see in your own homework assignment. That's a good way to brush up on those. All right, so what I'll start with is just talk a little bit about how we did on this. So the average this week for the homework assignment, the first homework assignment that we had, was 10.78 out of 12. So that's actually pretty good. We're, I like to compare year to year because the assignments don't change a whole lot from year to year. And this is about 0.4 points out of 12 higher than last year. So a significant improvement over last year. We do need to keep it up because the assignments get, more difficult and faster pace and things as we go along. So I can't reiterate enough that if you have any difficulties with this assignment, please make sure you get those questions and concerns addressed right away. Don't wait until the exam time or it'll be too late. All right, so let's get into the questions that I'm going to go through today. So we started, really, Chapter 1 starts with the mass laws, and the one that's the most difficult, I would say, is law of multiple proportions. So this question is basically just asking about the definition of the law of multiple proportions, or what are some of the statements that are included in that law. So according to the law of multiple proportions, then we have 4 statements, and as well as the answer, none of these. So what we have to keep in mind is sort of the key elements of law of multiple proportions. So in law of multiple proportions, we're talking about 2 or sometimes more than 2 technically, but 2 or more compounds. So that's sort of the first part of it. But the key is that these 2 or more compounds have the same elements in them. All right, so when we have 2 or more compounds that form from the same elements, that means we must have different mass ratios. Now this is not 100% true. We'll learn some things, probably not this semester, but later on in chemistry, and if you keep taking chemistry, that there are compounds that have the same mass ratios of elements, but are actually different compounds. But as sort of the the outside of chemistry and sort of understanding how compounds form from elements, the supposition was that if you're going to form 2 or more compounds from the same elements, what makes them different from each other is the mass ratios of the elements. And the example I gave many times in class was carbon dioxide, carbon monoxide. They both have carbon and oxygen as the only elements in them, but they combine the carbon and oxygen in different mass ratios, which then makes them into different compounds. So that's really the key sort of qualitative statements about the law of multiple proportions. And then the other thing too is that if we talk about the mass ratios of the 2 compounds, meaning the ratio of one element to another in the 2 compounds, I'm not going to give the full sort of mathematical treatment of this. We don't need it for this question. But basically, in the law of multiple proportions, if we look at the mass ratios of the 2 different compounds, those ratios are going to be related to each other by a whole number, I should say a small whole number, or simple fraction multiple. All right, and this sort of stems from the fact that when we're combining elements to make compounds, what we're really doing at the atomic level is combining discrete numbers of atoms to make those compounds, and so you can't have really any random ratio. The ratios are going to be sort of related to each other in pretty simple ways. So those are kind of the key statements. Now let's figure out in this question which of these four would be part of the law of multiple proportions. So the first one is that if the same two elements form two different compounds, which is sort of part of that, they do so in the same ratio. Now remember, as we said here, if two elements form two different compounds, they have to be different mass ratios. So that gets rid of that one. B, it is not possible for the same two elements to form more than one compound. That is also wrong, because that is, again, a key aspect of the law of multiple proportions. We're talking about two or more compounds that have the same two elements in them. The ratio of the masses of the elements in a compound is always the same. This is true, but this is part of the law of definite composition. So this is not a false statement, but it just doesn't apply to law of multiple proportions. Okay? So there are three mass laws. We need to be able to distinguish them. And even though this statement is correct for the law of definite composition, it is not part of the law of multiple proportions. That's why we're not going to include that one. And then D, the total mass after a chemical change is the same as before the change. This is also true, but this is part of the law of conservation of mass. So choices C and D are correct statements of mass laws, but they just don't apply to the specific one that we're talking about here, which is multiple proportions. Okay? So those three are all out, and that means E, none of the above. Now there is a bit of a psychological barrier to choosing none of the above as the answer that I'm aware of. You have to trust yourself to know these principles, know these concepts in and out, and indeed in this question, none of these was the correct response. Okay, so if we move into the next couple of questions, are going to deal with the Rutherford gold foil experiment. So there were a key few experiments that allowed us to determine the structure of the atom, the subatomic particles in particular that make up the atom, protons, neutrons, and electrons. A couple of these dealt with electrons. That would be the cathode ray experiments and the oil drop experiment. And then the key experiment that allowed us to sort of understand that an atom has a nucleus, a really dense center of positive charge, was the Rutherford gold foil experiment. So let's actually do these in the opposite order that I have them, because it makes a little bit more sense to do it this way. So the first question that I have here about Rutherford gold foil experiment, alpha particles directed at a thin metal foil, that's what the experiment was. Alpha particles being massive, positively charged particles. We don't need to know much more about their structure than that for now. And so Rutherford shot these very energetic particles at a thin metal foil. I think it was gold is what he used. And let's talk, this question just talks about what are the possible experimental observations. So again, what he did is he had a source of alpha particles, and he's going to direct them at a metal foil. Let's line those up a little bit better. So his alpha particles, and then they were going to shoot at a metal foil. And then as they passed through the foil, there were a few different observations. And so what turns out happening is that most of the particles go straight through. So that's going to be, most alpha particles don't change their direction at all. So that's one possible outcome. And actually, if the if the previous model of the atom, the plum pudding model, was correct, this is basically what would happen, is that all of them would go through. They would just pass right through. But what also can happen is that some of the particles get diverted or deflected to some extent, and then some of the particles go straight back towards the detector. They're completely reflected. So there are three possible outcomes here for the particles. They can either pass straight through, which is what most of them do. They can be deflected at a small angle, meaning their path is going to be altered a little bit, or they can completely bounce back towards where they started. And this part I didn't probably just explain as well in class as I could have, but basically the ones that pass through, they pass through because they don't collide with anything. The ones that are reflected are going to be the ones that collide with the nucleus. So this was basically how they figured out that there is a nucleus, is because in order for an alpha particle to completely reverse and change directions, it has to collide with something that's positively charged and very massive. And so that's sort of how they figured out that most of the mass was in the nucleus as well as the positive charge, was because of these reflected particles. Now the ones that are deflected at a small angle, I guess it's a little bit harder to say what exactly happened to those, but that can occur for a couple of reasons. They could occur because they get close to the nucleus and sort of just deflect off the side, but also it can be because they interact with the electrons. All right, so in a in a typical atom, you're going to have a cloud, as we call it, of electrons that surround the nucleus. And so if the alpha particle gets close to the cloud, it's actually going to be attracted to that cloud because of the opposite charges, the alpha particles being positive, the electrons being negative, and that can cause them to sort of deflect a little bit. So that part I probably didn't explain very well in class, but if you look at the answer choices here, then A is that it passes through without changing direction. That one can certainly happen. That'd be the ones that don't collide with any atoms, that just go straight through the empty space. B, be slightly diverted by attraction to the electrons. So in a small percentage of cases, they will be able to interact with the electrons, and they will be slightly diverted. So that one's also true. That's one I probably didn't explain very well in class. And then C, be reflected by direct contact with the nucleus. That's what happens in a small percentage of the particles as well. So all three of those are possible outcomes, and those are the correct explanations for them. So choice E would be the one that we want to pick, in this case, all of the above. Now that's what happens in the gold foil experiment. And the next question, going in reverse order for a second here, is sort of then understanding what were the conclusions that came from that experiment. So when you make those observations that I just described in the previous problem, what does that lead to in terms of the picture of the atom and some ideas about it? So he found that a small percentage of particles were deflected. That's what we just talked about. Which of the following was not accounted for by the proposed structure of the atom? All right, so basically what Rutherford's model led to, as we kind of already talked about, is that in an atom you're going to have a small nucleus with all of the positive charge, and then around that, in a very large area, mostly empty space, you're going to have the electrons sort of surrounding that. But again, they're going to be mostly empty space at any given time. So which of the following was not accounted for? So A, the small size of the nucleus. This one was certainly accounted for by the Rutherford model. That's really what the key thing that it showed. The charge on the nucleus. So because some of the particles were deflected, as this problem says, that basically means the charge of the nucleus has to be positive, because remember the alpha particles were positive, and basically for them to be reflected by the nucleus, that means the nucleus has to have the same charge, because like charges repel each other. The total mass of the atom, this one was not actually accounted for here, because the Rutherford experiment does not account for the neutrons in the atom. So if we recall, and we're going to talk about this more in a second here, the mass of the atom includes the protons and the neutrons that are in the nucleus. And Rutherford's model does not include neutrons. They didn't know about neutrons at that time. They weren't able to measure the mass of the atom, and they weren't able to formulate that there were actually neutrons in there that would contribute to the mass. So this one, I believe, is going to be our correct answer, because Rutherford's model, while it said that most of the mass, almost all of the mass in the atom was in the center in the nucleus, it didn't specifically say what that mass was. It didn't know that there were neutrons that also contributed to the mass. So that one's going to be the one that's not accounted for, or by the model proposed by Rutherford. D, the existence of protons. That again is because we now know that there are positive charges in the nucleus, so that was accounted for by his model. And the presence of electrons outside the nucleus. This sort of follows from the idea that if you have a nucleus, the electrons that are the negative charge must be then outside of that nucleus. So basically the Rutherford experiment led to this nuclear model of the atom, where you have a very small, very dense nucleus surrounded by electrons, but it did not account for the presence of neutrons, which would also then contribute to the total mass of that atom, especially in the nucleus. All right, so that's kind of takes us through those couple problems on subatomic particles in the Rutherford experiment. Those seem to be the only ones that we had a little bit of trouble with respect to subatomic particles. Now, there were a good number of questions on this this homework assignment that asked us to count the number of subatomic particles, so number of neutrons, number of electrons, and so on. And so there are a lot of variations on this, so you might not have gotten this exact problem, but there were a lot that were like this that we should understand how to do this. So the first one here is, what is the sum of the number of neutrons and electrons in the ion 73As3+? We can write that out a little bit more largely here. So this is the ion that we're considering. We want to know neutrons plus electrons. So we can get those in either order. The first thing that we'll need to be able to do this is we do need to know the number of protons as well. Now, we're not specifically asked for that, but the number of neutrons and the number of electrons are both related, as we'll see, to how many protons there are. And the number of protons we can always get, because that comes directly from the atomic symbol. So because it's arsenic, As, it's going to have a certain number of a certain number of protons in the nucleus that characterize it. So let's figure out what that is. And for this one, we are going to have to go to the periodic table. So let's go ahead and open that up. And so if we zoom in, we see that, I don't know why my highlighter doesn't follow me in this program. All right, sorry, I think I fixed that problem, so now you'll be able to follow my highlighter. So if we want to find the number of protons that are in arsenic As, we need to find it on the periodic table, which is right here. And we see, I'll zoom in a little bit further so you can see it clearer, that the number above that symbol in the periodic table, if you'll stop zooming, that'd be great, is, there we go. Oh, come on. All right, there we go, 33. I'm having a lot of trouble with Adobe today. All right, so it's atomic number 33, as you can see, the number 33 above there. So that means that arsenic has 33 protons. So if we go back to this, then the number of protons is going to be 33. We could write that in the symbol down here as the atomic number, which sometimes is shown, although it doesn't always have to be there, as we saw here. All right, so that's the number of protons. Now, the first thing we can get is number of neutrons. And what we'll recall is that this mass number here, abbreviated as A, is equal to the number of protons plus the number of neutrons. All right, and so we're told that the mass number of this ion is 73, and so that's going to be equal to the number of protons, which is 33, plus the number of neutrons. And with a little bit of simple algebra, we can figure out that the number of neutrons then is going to be 40. We just subtract the two. 73 minus 33 gives us 40 neutrons. So that's part of it, but we also need the number of electrons. And so for this, then, what we have to figure out is we start with, again, the number of protons, which is 33. Now, if this was a neutral atom, if there was no charge, the number of electrons would have to be the same as the number of protons. But because there's a charge, we have to either add or subtract extra electrons. This is a 3+ charge, which means we have 3 fewer electrons than protons. So anytime we have a positive charge, that means we've removed some number of electrons, in this case 3, because it's 3 positive charges. So we subtract 3, and that means we're going to actually have 30 electrons in this. So to get the +3 charge, we have 33 protons, 30 electrons, 3 extra protons and electrons. And so then finally, the sum of those is going to be 40, which is the number of neutrons, plus 30, which is the number of electrons. And then so for this particular question, the answer would be 70. And in this one, we have to, I believe, enter in the answer as a number. It would have to be exactly correct to get credit for this one. All right, so that's how we count subatomic particles. This one really dealt with all of them to some extent because we needed number of protons as part of it, number of neutrons, as well as number of electrons, and dealing with charges and ions, so a lot of stuff going on here. All right. This question here is similar. It probably does take things a little bit further than maybe is necessary at this point in the class, but there were a few questions on this assignment that asked us to count the total number of electrons in either a molecule or ion. Now, I really haven't talked about chemical formulas yet in any great detail, so there may have been some confusion on this that will get cleared up very soon. But essentially, if we have a chemical formula, it's going to have more than one element in the formula, and then the numbers are going to indicate how many of each of those we have. So if we have CH3 with a minus, let's sort of dissect this a little bit. So this means we have one atom C, which is carbon. The 3 next to H means that we're going to have 3 hydrogen atoms. So 1 carbon atom, 3 hydrogen atoms because of the 3 here. And then this means that we have a total negative charge on the whole thing. All right? So when we're adding up the number of electrons in this ion here, what we need to be able to do is figure out how many electrons does carbon have, how many electrons does hydrogen have, in this case 3 hydrogens, and then add 1 for the negative charge. So then to get the total number of electrons, what we're going to do is figure out how many carbon has, how many 3 hydrogen atoms we'll have, and then we're going to add or subtract because of the negative charge, in this case add because of the negative charge. All right, so let's go to the periodic table and figure out how many electrons carbon and hydrogen have. So if we go to the periodic table, we see that carbon is here, atomic number 6, so a neutral carbon atom would have 6 protons and 6 electrons, so it would be 6 from carbon. We have 3 hydrogens. We go to the periodic table. Hydrogen is the first element, number 1, so that means each hydrogen atom would have 1 proton and 1 electron if it was charged neutral. And so that's going to give us the first two parts of that. So as I said, we're going to have 6 from carbon. 3 hydrogens are each going to have 1 electron. And then we have to also account for the negative charge. And because the whole thing has a negative charge, that means it has 1 extra electron, so we have to add 1 more. So the total number here would be 10 electrons for this ion, CH3-. All right, so this was kind of, a lot of people here put 8, which would be the number if you subtracted 1 here. But because it's a negative charge, we have to add 1 extra electron. And so the total will be 10. Now again, it's maybe taking a little bit of a step forward that we haven't seen yet, but it is a good exercise to make sure we understand how to count electrons and atoms and then account for negative charges. As we start talking about chemical formulas and ions in more detail, we'll be able to answer this question much more easily. All right, and then we have one other question that I want to go over, a couple other questions, I guess, that are also on the topic of counting subatomic particles. So we want to know, what is the identity of element E if the E plus ion contains 18 electrons? All right, so E plus, we have 18 electrons. This one is working backwards now. So normally that if we gave you the charge and we knew the number of protons, we could figure out how many electrons there are. In this case, we gave you the number of electrons. We have to work backwards to find the number of protons. Now, as we said, when you have charges and ions, either positive or negative charges, that means you either have extra electrons or not enough electrons to balance the charge. So in this case, if it's a positive charge, we have 18 electrons. That must mean we have 1 additional proton, 19 protons. All right? Because remember that each proton has a +1 charge, each electron has a -1 charge. So if our total charge is +1, that means we have 1 extra proton. So E plus has 19 protons, and then we're going to use that to figure out what the atomic symbol is for E. So if the atomic number Z is 19, then the element that it's going to correspond to is going to be the one that has 19 protons. And so we're going to go to the periodic table and figure out which one that is. So in this case, we have to find number 19. They're all in order, so we just find number 19 here, and that's going to be K, which is potassium, and we just need to give the symbol here, K. So K would have 19 protons, and then with a plus charge, it would have 18 electrons, and so that's going to be the element we identify. All right, and I believe this one also, you just had to type in the symbol K, and that would be the correct answer. So here we just worked backwards. We didn't give you the atomic symbol. We had to ask, based on the charge and the number of electrons, how many protons are there, and then from there we can get the symbol. We didn't have to even deal with neutrons at all in this question. All right, and then the last problem here deals with in which of the following pairs of isotopes is the number of neutrons the same. So the long way to do this would be to go through each of these isotopes and figure out how many neutrons it has, which we know how to do, because remember that in these symbols, this superscript here, this number that's shown in the symbol on the left, is going to be the mass number A. A is the number of protons plus the number of neutrons. And then from there, we can figure out the number of protons based on the atomic symbol, subtract that from the mass number A, and that gives us number of neutrons. So if we wanted to, we could do this for all of them. Now, there actually is a shortcut we can take in a lot of these here. So keeping in mind sort of that this relationship exists, the mass number is the number of protons plus the number of neutrons, we can look at some of these and eliminate them right away without even calculating them. So if we look at choice A here, 3H and 3He, they have the same mass number A, but they have different numbers of protons because they're two different elements. And so if they have the same mass number, different numbers of protons, that means they must have different numbers of neutrons. So we don't even have to calculate those. We know they're going to be different from each other. Again, we're looking for the pair that has the same number of neutrons. Now, if we go to choice B here, this one's not as obvious because we have two different mass numbers and two different elements. So I think for B, we're going to have to actually calculate them out. So for 14 carbon, the mass number is 14. That's going to be equal to the number of protons plus the number of neutrons. So we have to find that on the periodic table. This time is C and N, carbon and nitrogen. C is atomic number 6, so it would have 6 protons. N is atomic number 7, so it would have 7 protons. So when we're calculating out those isotopes to figure out how many neutrons there are, for 14 carbon, there's 6 protons. And that means there would have to be 6 plus the number of neutrons equaling 14. That means the number of neutrons equal to 8. And then if we do 15N, the mass number for 15N is 15. As you said, nitrogen N has 7 protons, and then the number of neutrons would be added to that to get the mass number, and so in this case the number of neutrons is also 8. So these two are the same, so if we trust ourselves we can go ahead and select choice B and not go through the rest of them. The rest of these we can also eliminate fairly simply, because if we look at choice C here, we have the same element this time, F, with 2 different mass numbers. So A is different, but the number of protons is the same because they're both fluorine, F, and that means the number of neutrons has to be different. Okay, so these ones are going to be different from each other. If you have 2 isotopes of the same element, they have to have different numbers of neutrons. That's what the definition of an isotope is. If we go to choice D here, this is a lot like choice A, where we have the same mass number A, but 2 different elements, meaning we have different numbers of protons in each of them, and that means the number of neutrons must also be different for that to be true. So we can eliminate D, and then choice E, same as A and D, same mass numbers, but 2 different elements, which means we have different numbers of protons and then different numbers of neutrons to balance that out. So we can get rid of that one. So again, we could have gone through the math on all of these like I did here and figured out the number of neutrons, and we would have found that A, C, D, and E, the pairs have all different numbers of neutrons, but for choice B, they both have 8 neutrons, the same number, and so that's going to be the correct answer. All right, so make sure we review that. As I said, we're not going to do a lot more with subatomic particles. We will count electrons a lot in this course, but protons and neutrons after this, we're not going to see them a lot, but we do need to know at this point how to use atomic symbols to figure out the number of protons, neutrons, and electrons total in an atom or ion, as we saw in this homework assignment. So that was probably one of the more advanced topics here, so definitely review that if you had any trouble with those. And we'll be back next week with the first Chapter 2 assignment, which is going to probably be a lot more math heavy than this one, so we'll go through some different types of questions there. In the meantime, if you have any other questions on this week's assignment, please don't hesitate to ask me. I'd be happy to clarify anything for you, and I will see you guys in class later today.